So I'm gonna have basically a parallel structure in series with some other component. And Kyle, give me a number, 1, 2, or 3. All right. Was that the actual master set problem?
Yeah.
Kyle, I can't believe you picked 3.
You should do an inductor.
An inductor here?
Yeah.
Is that good for you? All right, so generally when you're dealing with a problem like this, I have 8 phasors that I need to put down. I have 2 phasors for each component. I have the voltage and I have the current. Recognize the uppercase, these are the amplitudes, and so they will be represented by the length of the phasor that we write down. The instantaneous values are usually lowercase, and those are projections onto the horizontal axis.
And that's if you're using cosine, right? Phase functions. If you use sine, it will be projection on the vertical axis.
Yeah. You gotta be careful about that because you have to sort of redefine where 0 is.
Okay, I see. That would make sense. Well, wouldn't 0 just be at the horizontal x-axis?
There.
Wouldn't it just be on the x-axis? Your 0?
It would be, but if you're using a sine function, then so you project it onto the y-axis, 0 degrees, I guess it would be 0. And then it peaks. Yeah, I'll buy it. But I'm going to use cosine. So we have some function here that my potential for the power supply is equal to some amplitude times the cosine of omega t plus phi. It's a generic equation. For our outlets, omega is, somewhere around 370, I believe, radians per second.
Yeah.
Phi depends upon what point you start the clock. And epsilon sub naught would be the magnitude, which was something I think 169.
For what?
For the amplitude of voltage coming over. It's 120 times the square root of 2,
Yeah.
whatever that is.
Like 1.4 something.
Was it?
It's like 1.4 something, the square root of 2.
We got the general, I guess if you have to know. Inquiry minds.
169.7.
169.7? Okay. So that would be epsilon sub naught for our power supplies here. All right, so when you're drawing down the first phasor, generally recommend starting out with something like this, with the more complex structure. I do know there's one thing that is going to be the same for these two, and that's going to be the voltage. So if I start out with the voltage phasor here, then, well, I killed 2 birds with 1 stone since the voltage is the same. And I generally like putting it into the first quadrant because that's just what my childhood scars tell me to do. And I think I had you do it at 30 degrees or pi over 6. So let's actually try to draw it closer to pi over 6. Perfect. Exactly pi over 6. So that is the voltage of R and the voltage of C. So 2 done. And now it comes down to the phasing that I know that for a resistor, current, probably better written, current and voltage in phase. For capacitor, current leads voltage. That's the ICE. And for an inductor, current lags voltage. And again, in the memory trick here, E comes from the term EMF, which is one of the uses we use in epsilon over there, which earlier textbooks had difficulty doing the Greek letters, and so they just used a capital E. The electrical engineering textbooks, at least the one that I had, used capital E for voltage.
You think of it like a EMF or electric potential.
Yep. All right, so from that, without doing much thinking here, I can immediately put down, since I have the voltages for R and C, I can put down the currents for R and C. And I had a stack of them, they're probably sitting right here, ready to bite.
Huh,
Can I take them into my office?
what?
My markers, what are they doing? You know, this is so neat, so I should be able to see them right off. Carry them back there?
Do you want the one in the jar?
No. No, those are, you know what? Just grab this. I probably walked, they're probably sitting around here in this room somewhere. But at least I'm filming my senility. All right.
Is that a word?
Senility?
Yeah.
It is a word.
Senile or something like that.
Would be the adjective. Senility is the noun. All right, so I know I sub R is in the same direction as V sub R because they're in phase. And for the capacitor, I know that the current leads. Now remember, these phasors are like arrows, like spinners that are all spinning around this central axis here. So they're spinning around like that. So when I say the current leads, that means it's in front by 90 degrees. So that should be a right angle there. This angle right here should be pi over 6. Because that is a right angle. Now the way this is structured here is I have current that's going to be flowing in this way and then it's going to split. I know this sort of thinking in DC terms that there is a direction. It will be flipping back and forth, and there will be times in which it's going one way for, say, capacitance and the other way for resistance or vice versa. But as a general conceptual idea here, what's going on, I have current coming in, it's going to split. In other words, the sum in equals the sum out. So I know that the current going across the inductor, and likewise coming from the power supply, must be the sum of these two. I was working with a student earlier who wrote, would be the equivalent of IL equals IC plus IR. And that's sort of misleading, because that makes it look like if we were thinking of this as sort of an elementary school problem, if IC is 2 and IR is 3, IL would be 5, and that's not the case. We add them like vectors. Unfortunately, we don't have a symbol really for a phasor. So we add them like vectors, so I'm basically adding these two arrows right here. Sort of parallelogram method, or I can put them head to tail, and we end up right here. And so the sum of those two is IL. Now, one of the mistakes I see students sometimes make is that they're adding them together, and they know it's going to be in that direction, but they draw it to here. No, draw it the full length. So the mathematical relationship, even though conceptually I'm adding two of them to get the third one, since I'm adding them like vectors, if I'm treating IL, IC, and IR as numbers, then it's Pythagorean theorem, because that is a right angle there. That is the correct mathematical relationship here. Another thing you need to be careful of, and this is something that I keep doing, is my L's and my C's look a lot alike here. So make sure it's clear. All right, so at this point, I've got 1, 2, 3, 4, 5 of my phasors down. So I've got my 3 currents, or I got the three component currents, not the power supply yet. and I have those two voltages. Now VL, I have one more relationship here I need to exploit, is the fact that the voltage leads the current. Well, there's my current, and voltage is going to lead that. By a 90-degree angle. So that is a 90-degree angle. And if you hadn't noticed, it's starting to get rather cluttered here. Hoping the different colors will sort of make it a little bit easier to see. I know that when I drew this on a piece of paper with the same color pen, it really looks like a mess.
Does it matter, like, how we draw the magnitude of voltage and current?
How you draw that one?
Yeah.
No,
Like, in comparison, like, for example, VR equal VC, then IR, should we always draw the current phasor less than the VR phasor?
I always draw the second one. If I had started with a current phasor, I would have drawn the voltage smaller, just because I find it easier visually for me, is that when I draw the second phasor to draw it shorter, because if I drew it longer, then I'd basically be writing over this one, and that bugs me for some reason.
Okay. So it really doesn't matter?
It does not matter. You're working in two different scales. This is in volts and this is in amperes, and so that's, you know, you really can't. Yeah, these are just representative of what's going on. So we now have VL. So the last thing is the voltages. Well, actually, we have the current for the power supply because that's the same as the current for the inductor here because they're in series.
And how did you find the angle for IL?
Say it again?
The angle for IL? Because we know like the representation of it, but how would we determine the
All right.
angle of IL?
So in terms of the angle here,
To the phase shift, I guess.
I know that angle there is pi over 6. Or if you prefer, radians or degrees, whichever one. I know that my omega here is going to be in radians per second, so ultimately it's going to lead towards what's the phase shift. Having it in radians probably makes a little bit more sense in the end. So to figure out what this angle is, basically what that angle is, I just need to figure out this one, the smaller bit, and just add pi over 6 to it. Well, this angle I'm just going to call theta. And again, I have a right triangle here. I know the tangent of theta is the opposite over the adjacent, which is IC over IR. And so theta is the arctan. Now, part of this depends upon what you're given as to what you do next. You find that angle. If you have the information, you can figure out easily the information for what the current across the capacitor over the current across the resistor, then you're golden there. You do that, you plug in the ratio, you find the angle. If you're not given that, if you're given the voltages instead, which is much more likely, then we need to do a little bit of manipulating here. So we bring in the other set of things that we know, is that the voltage across the resistor is equal to the current across the resistor times the resistance. Ohm's law. The voltage across the capacitor is equal to the current across the capacitor times the capacitive reactance, where X sub C is equal to 1 over omega C. The voltage across the inductor is equal to the current across the inductor times the inductive reactance, where X sub L is equal to omega L. This right here and this right here are not problem specific. They are the rules that we're working with. This is problem specific. Matter of fact, all of that is problem specific.
Those are all max values, right?
Pardon?
Those are all max values, right?
Yes, all the capital letters are max values. So in the master set, you're given enough, I think I gave you frequency and you find angular frequency.
Yeah.
So omega, you've calculated already in part 1. C and L are given, so you can find x sub C and x sub L. So back over here, since I sub C is V over X, so that's V sub C over X sub C, divided by, again, this is the arctan, I sub R, which is V sub R over R. And since VC and VR are equal, those will cancel out, and I'm left with the arctan of R over XC. That'll get me theta, and then I can find the actual direction this is pointing in at that point just by adding again pi over 6 plus whatever theta is. I sub C, the direction of I sub C in this problem, well, I know what IR is pi over 6, and then I add pi over 2. Once I have the direction of IL, I add 90 degrees to pi over 2 to get V sub L. Okay, questions to here, because we're about to hit the hard part. I think on part 2 of the master set, it's the very last question of question 2, which I consider the hardest part of the whole thing. All right, so we're going to get rid of, and that is a C, not an L. All right, we want to erase stuff. I'm going to keep that. What color is just gonna pop? Pink, of course. So I know the voltage across my power supply is gotta be equal to the voltage across here plus the voltage across here. So, well, I got my voltages there, I'm gonna add them, and I add them like vectors. To say that epsilon naught equals VL plus VR, again, misleading for the same reason as before. So in theory, that's a parallelogram. I've done worse. And so that's epsilon sub naught in pink there. And I'm not sure pop is really the word I would use at this point for that, but there it is. So let's sort of isolate what we have there. I know V sub L is shooting off that way in some direction. And VR is going in that direction somewhere. There's my epsilon sub naught. It's the sum of those two. Now in the master set, you've already figured out what epsilon naught is. I think that's problem 1A. All right, so what we know this angle here. So I probably should do some labels here. This is just pi over 6. This and I'll call that angle. So there, call that one phi. And I want to figure out what alpha is. And then ultimately, epsilon sub naught is alpha plus pi over 6 in this problem. So if I look at my quadrilateral there, what do you know about the sum of the angles? Is that good?
It should equal 360.
It should. And for a parallelogram, what's the sum of these two angles?
1980.
Right. So I know that this angle down here is just phi minus pi over 6. Because phi goes all the way to here, pi over 6 goes to here, and I want to know what's in between my VL and VR, or VC. No, VL, I was right, VL and VR. So this is going to be phi minus pi over 6. This angle, therefore, is 180 degrees minus that. Yeah, let's mix units. So that's pi minus phi minus pi over 6, or pi 5 pi over 6. No. That's phi minus pi over 6, and then I want pi minus that. So that becomes 7 pi over 6 minus phi, which is some angle. Let's call that beta. So that tells me this angle here. Now let's constantly zoom in on just this triangle right here. So I got VR, this length here is VR. This length here is VC. And this length here is, sorry, VL. And this length here is epsilon sub 9. I'm trying to figure out alpha. I know this angle here is beta, which in theory I already know what the number is, given enough information. So epsilon sub naught. So at this point, I'm trying to find this angle right here. I have some idea of the proportions of these sides, and so law of cosines kicks in. Epsilon sub naught squared is equal to VL squared plus VR squared minus 2 VL VR cosine of